Hello! This is the second video in the 7th chapter of the Crystal Clear Electronics videos, in which we will learn about mechanical switching device, including relays.
The first important thing is that we can switch these electronic switching devices not mechanically, for example with our hands, but with some electrical quantity, i.e. current or voltage.
Let's start with the relays. There are three main parts of a relay: the coil, the iron core, and the contacts. Let's discuss the coil first, which you may not know yet.
The relay is formed out of a long wire, which is wound around a geometric shape, usually a cylinder.
A tekercs az egy valamilyen geometriai alakzat, általában egy henger köré feltekert, hosszú vezetékből van kialakítva.
You may not know, but if current flows through the wire, then magnetic field will appear around it. We can use the right-hand rule to determine this.
Mágneses tér jön létre, ennek meghatározásához a jobbkész szabályt tudjuk alkalmazni.
If you're interested in more details about this phenomenon, you can look up the Ampere's law on internet. For now, all we need to know is that when current flows through this wire, a magnetic field is created. This field is very small. But for example, if I wind the wire on my finger, the magnetic field of the wire will add up, you can always imagine the right-hand rule, and a much stronger field is created. The more threads I wind up, the bigger the field will be. And you can make it even bigger by sliding an iron core into the middle of the coil. This raises an interesting question that many of you would think that this is a plain copper wire in the relay. However, not quite, as it is constructed from a copper wire with lacquer insulation. And the role of this is that if we didn't have this insulation, we'd have a short circuit between many wires side by side. Because the current would not go all the way through the coil, but would flow from one outlet to the other, which is not suitable for us. This varnish insulation allows us to wind a lot of wires in a very small space, because it does not take up as much space as, for example, the plastic insulation you see here on this long red wire.
And now let's discuss how these things are connected to the relays.
A coil with an iron core has two terminals, which form part of our input stage. We're able to move the moving contact by the magnetic field, which is created by flowing electricity through the relay. The output stage, which we can switch, consists of terminals and contacts. The left side of the picture shows the input stage, the right side shows the output stage. The number 1 marks the terminals of the input, the number 2 marks the terminals of the output. Its operation is very simple. If we connect proper voltage to the input stage, then the tilt switch of the output stage will draw to the other terminal because of the magnetic field which is created by the current that flows through the coil. The relay used in the curriculum can be seen quite clearly in the individual parts. On the left side, you can see the outputs of the input stage, i.e. the iron core coil outputs, and on the right side, the outputs of the output stage, i.e. the contacts outputs. You can also observe the moving contact. This is what is moved by the magnetic field created by the coil. You can also see that there is the iron core coil and the spring that retracts the moving contact.
However, I do know that not all relays look the same, and there is no return spring in all of them, for example in the bistable versions.
Yes, latching is also called the phenomenon where the contacts retain their status after the magnetic phenomenon has stopped to exist. This is how bistable relays work, which have two types depending on what control they require. In the first case, our control circuit also has two terminals, as before, and the direction of the current that flows through the coil defines to which stable state will our output stage be set. In the second case, the structure of the input stage is different, because in the present case, it contains two coils, which can be seen in the schematic figure. Coil number 1 is capable of moving the controlled contact in one direction, as previously known. To set our contact to its default place, we need to connect proper voltage to the coil number 2, which is capable of pulling in the contact to the other direction. You could consider it as we have a setter, set or S, and a resetter, reset, R coil. Usually, in the datasheet of latching relays, the manufacturers use the markings S and R, and because of that, I'll refer to them the same way. The symbols known for mechanical switches can also be found in the case of relays for output stages. If we combine the bistable and DP-DT output stages, then the internal structure will look the following way. Let's look at this device's operation to help understand it. C number 1 and C number 2 terminals are common contacts or poles. These can come in contact with pin A or pin B. As we can see, with the dotted line in the figure, C1 and C2 depend on each other, so they can be switched at once to direction A or B. So this is our output stage. Our input stage contains two coils because of its bistable operation, a set and a reset coil.
Let's take a look at how this looks during operation.
Suppose that the C pins are in contact with the A pins by default. If we connect appropriate voltage to the set coil, then the C1 and C2 contacts draw to contacts B1 and B2. After eliminating the voltage, the contact C will stay in stable state by still in contact with pins B. If you want the terminals A and C to come into contact again, you'll need to connect appropriate voltage to the reset coil. Once the voltage has been removed, the contacts remain similarly stable. You can see this process in this table. We connect the voltage to the set coil, C1 and C2 are connected to B1 and B2. Then, even if the voltage on the set coil is removed, C1 and C2 are still connected to B1 and B2.
Because this is a bistable relay.
That's right. However, if you then apply voltage to the reset coil, the C1 and C2 moving contacts or poles will flip over and now connect to contacts A1 and A2. Then, if we remove the voltage, the connection between C1 and A1 and C2 and A2 will remain the same due to bistability.
You may ask what the relays are for. What do we use them for? Let's talk a little bit about that.
We often use relays if we would like to switch higher voltage using small voltage, for example 12 volts. The higher voltage can range widely between 24 to 230 volts. There are such relays which are able to switch tens and hundreds of amps as well, while we only have to transfer a fraction of the power through their coil. This allows you to switch a much higher current by small current. For example, here is this relay. It has a rated current of 500 amps, and it's used, for example, for the positive and negative battery outlets in electric cars. Here you can see this other relay. It can handle 100 amps. The interesting thing is that you can even manually switch the two states. This is a bistable relay. You will see later on that microcontrollers, microprocessors, which we can control and program, typically operate at low voltages, i.e. a few volts. If we want to use them to control the lights at home, which operates at 230 volts, we will most likely need relays. Another important role of relays is the galvanic separation, which you can learn more about in the written material.
That's all for this video, but don't go too far, because in the next video we'll continue with another type of electronic switching device, the bipolar transistor. Bye!
Sziasztok!